Now we start our practical lesson number 3. Today's laboratory work, and write down to your notes the aim of our lesson, the theme of our laboratory works, a study of the roughness of machined surfaces of the part. Study of the roughness of machined surfaces of the part. The purpose of the work is to establish the relationship between the roughness of the machined surface of the part and the modes of machining. And equipment, instruments, and accessories. Its laboratory table, samples of part from it's made from steel 45, are cylindrical in shape, divided into separate sections by annular grooves and machined in different modes. And third, its profilometer, TR 200. So write down to your note the name, the purpose of the work, and equipment, instruments, and accessories. And to where we can take our part with separate section. And this part must be machined in different modes. So we use the lathe, screw cutting lathe machine. And then please write down to your notes brief theoretical information about roughness and about our laboratory work. When processing workpieces or parts with a blade tool, the surface roughness largely depends on the cutting speed and fit. The depth of cut has little effect on surface roughness. It has been established that after processing a steel billet at a cutting speed of V equal 20 meter per minute, the greatest roughness is observed, which is associated with the phenomenon of active build-up formation on the cutting part of the cutter. At cutting speed above 80 meters per minute, build-up age practically stops. In addition, at high cutting speed, the depth of the plastically deformed layer is significantly reduced, which also reduces the roughness. A change in low cutting feeds, up to 0.2 millimeters per revolution, slightly affects the change in surface roughness. But when moving to the feed range of more than 0.2 millimeters per revolution, the micro roughness of the machine surface increases more intensively. Now in figure 3.2, you can see the process of cutting. The following parameters are used to estimate surface roughness that you can see in figure 5.3. So the surface roughness is longitudinal treasured in the direction of the cutting speed vector, and transverse measured in the feed direction. So the following parameters are used to estimate surface roughness. The height of profile irregularities, R suffix Z, is the average distance between 5 peaks and cavities on the curve of surface irregularities. You can see irregularities in the figure 3.3. You must find on this figure 5 peaks and 5 cavities. For example, first, second, third, fourth, and fifth. And cavities, first, second, third, fourth, and fifth. Then you use the formula on this slide, and you can calculate RZ, the height of profile irregularities. It's a first parameter that used to estimate surface roughness. B, the greatest height of irregularities, R suffix maximum. The distance between the line of profile peaks, this line, I'm shown on the figure, first line of peaks, and the line of cavities. And distance between two lines, its parameter R suffix maximum. It's greatest height of irregularities. All this within the base length. Base length is this distance on the figure, big L. It's base length. Base length of surface. Next parameters. Arithmetic mean profile deviation, R suffix A. RA determined from the absolute values of the profile deviations H from the midline. You can see in this figure the midline. It's midline and small h and big H. For first peak, H1, no, you can see H1 like this. H1, H2, H3, H4, H5, H6, H7, 8, 9, and etc. So you can have many H's, many values of H. Then you use the formula to calculate that we use to calculate parameter R suffix A. It's arithmetic mean profile deviation. We use all these H, the sum of H, and we divide by the number of these parameters. The average step of the asperities S suffix M and the average step of the asperities over the peaks SM, like in this figure. And one more parameter that estimates surface roughness is the relative reference length of the profile, T suffix P, the ratio of the reference length of the profile to the base length. We use the formula on this slide, T suffix P. In this formula, nu is the reference length of the profile equal to the sum of B suffix I. For example, it's B suffix 1, B2, B3. So the sum of this B will be new, and we use this new in the formula to calculate T suffix P. And what is L? L is a length of the profile. The sequence of our laboratory work. Install the test sample in the prism. In figure 3.4, you can see our part. It's our test sample part. You can see first, second, third, fourth, and fifth surfaces. These surfaces was machined with different modes, and roughness on these surfaces are different. So install the test sample in the prism of the profilometer. Profilometer, it's a device that you can see in figure 3.5. It's general view of the profilometer TR200. The device is called profilometer. It's our example part, and its device TR200. The sample machined in the following cutting mode. Feed S is equal 0.1 millimeter per revolution. Cutting depth T is equal 0.5 millimeters, and cutting speed varied from 10 to 130 meter per minute. And then that parameters that we measuring, we must write down to the table 3.1. Table 3.1 you will see in the next slides. Now, elements of the device TR200. 1. Its device. 2. Its sensor. 3. Position 3. Its sample plate. Position 4. Display. Position 5. Power button. Position 6. Start button. Position 7. VF button. Position 8. Exit button. Position 9. Menu button. We use this button when we need to change our menu. And position 10. Scroll button. Up and down. And position 11. Enter button. Enter. Preparate the TR200 roughness tester for measurements. portable roughness tester TR200 that you can see in figure 3.3, 3.3, 3.5 and 3.6 refers to probe instruments designed to work in production conditions and can be used to measure the surface roughness of various machine building parts. The method calculates the roughness parameters in accordance with the selected method and displays the profile graph and all measured parameters on the LCD screen. This device can measure the following parameters that characterize the surface roughness. As you can see, this parameter R suffix A, R suffix Z, R maximum, and other parameters. When measuring surface roughness, a transducer is placed on the part and swept across the surface at a constant speed. The sensor perceives surface irregularities with a sharp pen. Surface irregularities cause a displacement in the sensor, which changes the inductance of the coil, generating an analog signal proportional to the dimensions of the irregularities. The signal is fed to a phase-sensitive rectifier. After amplification and conversion, this signal enters the data acquisition system. The collected data is digitally filtered, and the digital signal processing chip calculates the parameters. To adjust the position of the device relative to the controlled part, a special stand is used, which makes it possible to ensure the necessary accuracy of measuring roughness on surface with complex shapes, like in figure 3.7 and 3.8. It's installation of the sensor on the surface of the part. You can see the sensor, its sensor of our device, and the surface of the part. When our sensor is moving, our device is measuring the roughness of our surface. So you can see the screen of our device of TR200 and process of selecting a menu item for changing measurement conditions. We use first button and then we can change the measurement conditions. Next screen of the device screen, it's on the figure 3.10, changing the length of the assessment. Then changing the measurement standard. We use standard, for example, ISO, standard ISO. Then setting the range from minus 20 micrometers to plus 20 micrometers. It's our range of measurement. Then we can make setting the displacement parameters. In our case, it's display R. We use parameter R suffix A. Then selection of the system of measurement units. We use metric system in micrometers, metric system. And then we can do setting the pen position. The pen position on the 0. What is the pen? Pen, in previous slide, on our sensor. There are the pen on the sensor. It's the direction of the pen, relative surface of the part. So, after changing all measurement, after changing in measurement conditions, we can start to measure the roughness of the machining surface in all areas of the part. So what we must to do? Measure the roughness of the machine surface in all areas of the part. Record the measurement results in table 3.1. Table 3.1, measurement data of the roughness of the part when the cutting speed changes. You can see we have constant feed and constant cut depth, cutting depth, or depth of cut. Then install in the prism of the profilometer the studied sample of the part which is machined in the following cutting mode. V is equal 60 meters per minute, so V is constant. T is equal 0.5 millimeters. T is constant 2, its cutting depth. And the feed varied from 0.15 to 0.60 millimeters per revolution. And measure and we must measure the roughness of the machine surface in all areas of the part. The result, and then we record the measurement results in table 3.2. Table 3.2 is the next slides. Table 3.2, measurement data of the roughness of the part when changing the feed. Feed is changing from 0.15 to 0.75 millimeters per revolution, and V and T is the constant. Are constant. Then install in the prism of the profilometer the studied sample of the part which is processed in the following cutting mode. V is equal 60 meters per minute. T, it's not T, it's S, big S, its feet is equal 0.3, and the depth of the cut varied from 0.3 to 1.5 millimeters. Let's change. It's not T, it's S, the feet. In millimeters per revolution. Then measure the roughness of the machine surface in all areas of the part. Then enter the measurement results in table 3. Table 3.3, measurement data of the roughness of the part when the cutting depth changes. So cut the depth is changes from 0.3 to 1.5 millimeters, and cutting speed and feed are constant. The values of this parameter constant is equal constant. So repeat steps from 1 to 9 for all studied materials. And position number 10, construct graphs of the dependence parameter RA from the V, from the S, and from the T. RA from cutting speed, roughness from feed, and roughness from depth of cut. The procedure for working on the profilometer is given in the instructions. Now I want to show for you the video about how to use the profilometer. Wait a minute. Video for laboratory work 3. Can you see this video?
This is a little bit lengthy of a video. It's approximately 18 minutes. All of the information that you're going to need to write your CFQ, you absolutely will know what it means. And I will go through this step by step at the end of the video. Okay, let's get started right now. Warning, viewer discretion is advised. This video is basically spacing of repetitive surface irregularities. So in other words, the tooling marks that your tool makes. Roughness height is basically the height or the depth of your cut, and some older tradesmen will also call this the scallop depth. Lay or lathe direction is the predominant surface pattern. So basically the marks that your tooling makes on the actual part. We're going to be going into this a little bit more in depth later on in the video. Roughness width is the distance parallel to the normal surface between successive peaks and ridges. Wave height is the distance between the peak and the valley. Sampling length, roughness width cutoff. Basically, this sounds a lot more difficult than what it is, but it's just the distance that we're measuring over. And later on in this video, when I do a demo using the surface roughness tester, it's the amount that the probe travels in and out. Flaw is an irregularity that occurs in a surface due to cracks, blowholes, ridges, scratches. Basically anything that's not in the machining pattern. There is no finished symbols for flaws. A special note should be included on the drawing where no flaws are permitted. Typical ways of obtaining surface roughness measurements is RA, RQ, and RZ. And here's a brief explanation of each. RA is probably the most popular we're going to use. RA is the roughness height, I'm going to butcher this one, arithmetical average. So basically what happens if you take a look at A, B, C, D, E, all these lines have heights or distances. So basically what happens is you add them all up. In this case, if you take a look, it equals 108. So you take 108 and there's 18 spots. So you take the average of them and it's 6. So that's how we calculate the RA. And in this case, with these measurements, the RA would be 6. To help clarify things, RA, RQ, and RZ is just a setting that you're going to be using on the surface roughness tester, and it will do the equation for you. RQ is the root mean square, so roughness height. Just like on the RA, we have 18 lengths. So what we're going to do is we're going to square each length, and then when we total them up, we're going to get the square root from it. So in this case, RA for the same measurement was 6, RQ is 6.4. RZ is the measurement of the 5 largest peaks compared to the 5 lowest valleys over your sample length. Material removal symbols. Identical surface texture all over. This is one of the newest surface texture symbols, and you probably don't have it in your textbook. But that little circle around the bent elbow means all over. Surface may be produced by any method. When this symbol is by itself without any accompanying symbol like a lay symbol, it can be produced by any method, meaning any type of machining. Material removal required. This symbol is usually accompanied by other symbols such as lay. Material removal prohibited. There are multiple reasons why they use this symbol, but one of the more popular ones is that surface is a datum for internal reference dimension. Basic surface texture symbols. Roughness average value. This can be stated in micro-inches or micrometers or roughness grade. Using the visual comparator, you can see on the top, which is micro-inches, and on the bottom, which is micrometers. Minimum and maximum roughness average value. This can be stated in micro-inches, micrometers, or roughness grade as well. By using the visual comparator gauge, if you take a look, the red would be the minimum and the blue would be the maximum roughness. So in other words, as long as you're between these two finishes, your part would be approved. Machining allowance to be stated in inches or millimeters. So this means that they left material on this surface to be removed, usually on castings or on material that have to have a certain amount removed off to prevent warpage, such as cold rolled steel. Maximum wave height can be stated in inches or millimeters. Basically, it is the height of the wave between the peak and the valley. Maximum wave spacing can be measured in inches or millimeters. It comes after maximum wave height. And what it is the measurement of the wave highest peak to the next highest peak. Roughness sampling length. Basically, this is the length that you set your surface roughness tester up to measure across. The minimum length, if not stated, will be 30 thousandths of an inch. Lay symbol, the direction of the predominant surface pattern. Lay symbol perpendicular. Lay perpendicular to the line representing the surface to which the symbol is applied. Lay symbol parallel. Lay parallel to the line representing the surface to which the symbol is applied. Lay symbol radial. Lay approximately radial relative to the center of the surface to which the symbol is applied. A lot of older tradesmen will refer to this as a Blanchard ground symbol. Lay symbol angular. Crossed in two slant directions relative to a plane of projection of the view in which the symbol is used. Basically, it looks like the cross section of a honed cylinder. Lay symbol multi-direction. An example of this finish would be, let's say, the bottom of a pocket that was machined by an end mill. Bunch of cross swirls, lay symbol, non-directional. This is usually produced by an EDM machine or a sandblaster. Lay symbol circular. Approximately circular relative to the center of the surface to which the symbol is applied. This symbol surface is most commonly associated with facing on a lathe. Conversion charts. Take a look at this conversion chart. An RA in micro-inches of 8 is equivalent to an RA in micrometers of 0.2 and a roughness grade of 4. Surface roughness comparison chart. This can be a little bit difficult to explain, so please bear with me for a few moments. Sometimes an engineer on a drawing will not put the actual finish that they want. They will turn around, they will say they will require a mill finish. So a mill finish in micro-inches is a standard between 250 and 32, so in the yellow. Now the possible parameters is 1000 all the way down to 8, but the acceptable parameters is 250 to 32. So therefore, if an engineer puts mill finish required, he wants a milled finish with a finish variable between 250 and 32 micro-inches. Visual surface finish comparator. Let's talk about the visual surface roughness comparator. And that's what we have right here. This guy's an awesome visual tool or visual reference for apprentices because it allows them to be able to see right away what type of finish they're getting while they're machining, which is kind of cool. These are not to be touched. Everyone wants to touch them. Oh, I'm running my fingernail up and down them. You're not going to get a super true reading by running your fingernail up and down because they have a bit of a coating on them. Although this guy is nickel, made out of nickel because it's a nickel plated process, how they actually make these. This visual comparator here if you look really closely right here, there's actually a hair stuck inside of this sample. How I know this is because I ran the surface roughness tester over top, and I wasn't getting an accurate reading for what the actual specimen was saying. Now, that doesn't mean that it's out. It just means how I know this is.
So you can see in our video roughness tester, but it's named profilograph or profilometer. So we use this device to measure the roughness of our surfaces of the part.
Because I ran the surface roughness tester over top, and I wasn't getting an accurate reading for what the actual specimen was saying. Now, that doesn't mean that it's out. It just means that there's a slight coating on top of it to protect it. But the visualization works great for these guys. Some of the tools that we use to check, you can use a microscope. A microscope's good for a couple of different reasons, because you can project it onto a large screen, which works great, and you can also record the image that you have. If you're in a hurry, an eye loop works great. You can also pick up a pair of these funky glasses. They work great. You can use different focuses, and they have their own light source. And you also have the good old-fashioned trusty magnifying glass with lights. I like using this one myself because it's just a little bit easier. So let's take a look at a specimen here. So I turn around and I have a block that's been ground. So I want to see what this actually is. So what I would do is I would hold my piece up against here. I would go down to the ground symbol here, and I would look at it and I would say, I only have two options for ground image or ground surfaces here. I got a 6 and I got a 16, or sorry, I got an 8 and a 16. Neither of them are as fine as what I have ground on here. So it's going to be less than an 8. So let's turn around and use this visual comparator here. And if I look here, I have a 3 and a 2 and a 4. So I got 7, 6, 5, 4, 3, 2. And I take a look here. We go this way here. And I would almost say between the 4 and the 3. And it's so close it could even be a 2. So I'm going to say between this range right in here. So how do I know what it actually is for sure? Because this is only a visual reference. It's a reference tool. So what I would do is I would take this guy here, set it on here, go start. You see this guy moving inward, then it's going to move outward. 3, 4, 3, 7. Let's look at our conversion chart. 3.7 converts over to a roughness grade of 3. And that looks basically what we have, a number 3 roughness grade. Okay, let's try another sample. Okay, so what we have here is the inside of a hard drive. This is a hard drive disk. Let's give it a try and see what we have here for a visual comparator. So we go through and we find our grinding here. We got 8 on the grind. So if we take a look, we can see clearly that this finish is much greater than this finish here. And then they only get rougher up to that point. So it's better than an 8. So let's take a look at our other chart here. Put this down here. I'm going to say it's better than a 2 as well. So let's measure it and see what it actually comes out to be.
Please look at the process of the measuring. We use our profilograph or profilometer. We push the button start, and then our pen is moving on the surface of our part, and then we can see the result of measuring on the screen, on display. It's process of moving, and now you can see on the display 0.4 micrometers. It's the result of
It's 0.4 and the
measuring of the roughness of our part.
L2 lap is pretty much the same as what we have. Profilometer or
Profilometer
surface roughness tester. So
or
why do I keep
surface
calling this a
roughness tester?
Because that's what Michitoyo calls it. This also comes with precision reference specimen. If you looked at this, we used this earlier today when we calibrated the machine. For extra references and zeroing and changing the different parameters, we use these buttons here. When we flip it over, if we push backwards, this guy will be released, and we can also unplug this. Now you can mount this to a surface gauge or any other type of piece of equipment. Then use this extension cord to go from here back into the unit. So 119.7, and this guy's supposed to be 120. It's 0.3 off. When you have one of these electronic units, it's really easy to switch between RA, RZ, and RQ just by switching.
Switch between RA, RZ, and RQ.
Surface roughness tester, skidded versus probe. But what I want to talk more
You
about
can see
is
the
stylus
pens
on the end here.
of surface roughness tester.
By switching the parameters. Surface.
You can see in different planes. You can see the pen of surface roughness tester.
Roughness tester, skidded versus probe. But what I want to talk more about is the stylus on the end here. If you take a look, you see that there's a tiny little needle sticking out the end there. That tiny little needle is actually what feeds back information into the system. But this is called a skidded type probe because it actually rides on the bump that's here. This can only check flat surfaces. It can't really check tapered surfaces or round surfaces. Now, if you have just the individual stylus sticking out, a non-skidded type, what happens is you can check round surfaces, tapers, and a few other things. But with this style, you're limited to only checking flat workpieces. Surface roughness tester setup. It is important to be perpendicular when you're setting this up. If not, you'll get cosine error. And if you're unsure of what cosine error is, check out my YouTube video, Cosine Error Explained. With a skidded probe, it is very important to be parallel to the surface to which you're checking. Not so much with a probe style, but with a skidded, it is extremely important. Checking the surface finish of a circular object. It is not possible to do this with a skidded style. It is possible to do it with a probe, though. Checking the surface finish of a groove. It may not be possible to do this with a skidded stylus due to space restraints compared to a probe. There are many different ways of measuring surface finish, including this optical profiler. There's also lasers. I almost feel silly taking this up because I know that just by going through this, you have an understanding of how to actually answer this question. But let's go through it anyways. Let's work our way from left to right. Let's start with the 60 thousandths of an inch. Position, it means machining allowance. I am required to take 60 thou off of this surface. Next up is 63. In this position, it's RA. My roughness average needs to be 63 or better. Here's what a roughness average of 63 looks like using a roughness comparator. Next up is the 3 thou on the top. The maximum wave height can be 3 thou. So the depth from the peak to the valley can only be 3 thou in depth. Next up is the 5 on the end. The 5 is really 5 thou, and that's the maximum wave spacing. So it's from peak to peak, can only be 5 thou. Next up, it looks like an equal sign on the bottom. That equal sign is the lay symbol for parallel. The machine finish is parallel to the surface that this is applied to. Next up is the 30 thou on the bottom right-hand side. This is the roughness sample length. As shown earlier in this video, you can set the sample length using the surface roughness tester. I'm glad to see that you enjoyed the video.
And now we are returned to our presentation. So what you need to do in our laboratory work number 3. Content of your report of this laboratory work. First, name, purpose of the work, device, and tools. Then, submit the results of experiments in the form of tables. You have the 3 tables, and you need to write down to these tables the results of measurements. Where you can find the results of measurements? It's the last slide. On the last slide, you can find the results of measurements of the roughness. Use these values of parameters. Then you need to calculate average parameters for each rows. And then you need to plot graphs of the depends of roughness on feet. It's first graph. Second graph, dependence of roughness on speed. You use table 3.1 and average parameters. And the third, the dependence, graph of dependence of roughness on depth of cutting. And you use table 3.3. Average parameter and its parameters of roughness and depth of cutting. So, what you need more? You need to write down to your notes figure 3.3 and formulas RA and RZ. RZ, RA. So you can start to make your report by laboratory work number 3.